Let's look at the controller blocks of the telediagram program together. First, we will discuss the hysteresis block. To input a value into the input of the hysteresis block, let's take a word register. It works by comparing the value at the input against the lower and upper threshold values and ensures that the data stays within that range. It then produces either a 0 or 1 at the output depending on this. Let's enter a lower threshold of 20 and an upper threshold of 90 and test this with a simulation. Let's start inputting data. Initially, we sent a value of 21, which is between 20 and 90, and the output is 0. Let's send a value of 90. The output is still 0. As soon as it exceeds 90, it will switch the output to 1. Now let's gradually reduce it. We sent a value between 90 and 20, and the output is still 1 until it drops below the lower threshold. Thus, the on and off operations can be managed within the threshold range. We sent another intermediate value, still 0. It will return to 1 as soon as we exceed the upper threshold again. This is the working principle of the hysteresis block. You can also trigger the trigger input inside with trig active operate. Next, let's look at the FBD controller together. First, the data inside can also be entered from outside. There is a setpoint. For example, we can define the setpoint inside or enter it from outside. We have an area where we set the data sampling time. If we know the KP, T, TD values for the FBD, we can enter them here. Or, by setting it to auto-tuning mode, the value connected to the Pro input is analyzed by the PLC and the KP, T, TD values are presented to you on the microterminal. You can also run it in automatic mode. As seen here, you can also enter data from the inputs. You can define the minimum-maximum values for both the input and the output. For example, if the min-max range of the value connected to the Pro input is 0 to 1000, you can enter a value of 100 here. FBD control will be performed within the range you set, including the minimum and maximum for the output. Here we choose whether the direction is forward or reverse. For example, if you are taking a 4 to 20 mA output or a 0 to 10 volt, you can enter this range. The direction, whether forward or reverse, can also be selected here. We can use the FBD output in this way. For example, you connected an RTD temperature input to the Pro input. You write the desired temperature value for this RTD PT1000 sensor. What will be controlled next? A servo motor can be driven, or a different control can be implemented, or analog control can be performed by connecting an analog output and managing your FBD controls in this manner. According to this analog output, control can be done either with a 4 to 20 mA current output or a 0 to 10 V voltage output. Now let's move on to the analog ramp block. Sometimes, if control over a driver with frequency is required to direct motors, the current value might need to be gradually increased or the voltage value increased slowly. In such cases, a ramp might be necessary. For example, let it reach from 0 to 10 but take 30 seconds to do so. Therefore, 30,000 milliseconds are entered in terms of milliseconds. Let's start the simulation. Now, as you can see, when we press start, it tries to reach from 0 to 10 in 30 seconds. It stops when it reaches 10 after 30 seconds. You have the option to enter the start and end times from outside. We have the opportunity to control it in this way. As you can see, it will progress to 6, 7, and eventually to 10. Let's look at it when it's completely done. Yes, it reached 10. So, we have performed a ramp process of 30 seconds. Let's move on to the next block, the on-off controller. This resembles hysteresis. Again, there are lower and upper thresholds. These thresholds also have a hysteresis threshold value, and how long it takes for the alarm to turn on and off can be determined here. Based on what will the thresholds be determined? Is it between, larger, or smaller? Later, will it be greater than or equal to, less than or equal to? We will select the between type in this section. Let's do another example. We connected word register to the INA input. Let's set the values for the lower and upper threshold inputs from outside. We connected a block to the threshold value of hysteresis. We also connected blocks to the turn on and turn off inputs for it to trigger the alarm. We will set the value in milliseconds from outside. Let's load this project into the device. We reconnect to the device via TCP. Let's perform the on-off controller tests with online monitoring. Online monitoring is active now. We entered 20 for the lower threshold value and 30 for the upper threshold. We said if it's between 20 and 30. Now let's talk about the value we will send. For example, we sent the expression 21 and the on-off control output became 1 because it is within that range. When we sent a value of 31, which is not between the values, we saw that it switched to 0. Let's enter 5 seconds for the alarm turn-on time. Let's also define the turn-off time. Let's enter that as 3 seconds. For example, we sent the expression 25. As you can see, it did not turn the output to 1. It waits for 5 seconds and turns the output to 1 at the end of 5 seconds. Now let's move outside the range. For example, we sent 18 instead. This time there will be a delay of 3 seconds. At the end of 3 seconds, it will drop to 0. Let's talk about threshold hysteresis. What happens when there is a binary deviation, when there is threshold hysteresis? Let's look at this together. Now let's send a value. For example, 21. Since it's within the range, it should turn on. Let's reduce the times to 0 for better perception. For example, the value range is now above 20, a binary hysteresis was made, and as you can see, it opened the threshold hysteresis value. So, it accepted it because it exceeded 20 plus 2. Similarly, we also did 30 plus 1. It remained at 1. But when we sent an expression like 33, we saw it drop to 0. You have the chance to add an extra threshold hysteresis value to the lower and upper thresholds. Let's give another example. For example, it accepted the value 28 in a binary drop. Next, our block is the change detector. The feature of the change detector is that it is a block that performs an operation based on the value connected to the upper input, according to level or percentage differences, and sends an instant trigger to its output. As an example, we added a block with a level change of 5. We added another block with a 50% change, and let's test this. With the up-down counter, we may not be able to instantly see the triggers sent in simulation. Therefore, by connecting the up-down counter block, we have the opportunity to observe whether it really generates. Now let's send a value. Currently, both triggers increased. Because a change of 5 occurred and a 50% difference occurred. Let's perform operations on this. For example, when we reduce the value 20 to 18, we observe no change in either. When it's 15, we again observe no change. But when it's 14, because there is a change of 5, it triggered. But since a 50% difference did not occur below, it did not send a trigger. For example, if we go below 10, that is, half of 20, yes. When we dropped to 9, a 50% change occurred, so it sent an instant trigger regardless of increase or decrease. Let's do one more example. We drop to 8. Because it dropped from 14 to 8, a difference of 6 occurred, so the upper part triggered. Now let's go below or above 9. Now the value 13 came. A difference of 4.5 is needed. So, when the value was 14, as you can see, both the upper and lower sides experienced an increase. You can use controller blocks in your project in this way.